Thank you very much. I forgot my phone to time it, so if I talk too short or too long, somebody will give me a sign. Nice to see everybody. My name is Heather Katz. I'm a professor at the University of Wuppertal since 2 years now, so I'm learning how to do it a little bit. But what I want to present today is work that I actually did while I was working on my PhD, or most of it anyways, and that was at the Technical University of Munich. Some of my old colleagues are here today, so it's nice to see everyone again. I would like to start with a little bit of a motivation. Why do we want to simulate bicyclists? Why is it important to have realistic cyclists in our simulation models? This is a pretty old picture. I took it right when I started my PhD in Munich, so 10 years ago. But even then, before we had these booms from COVID and more people turning to cycling, we had the situation like you see in this picture that cyclists were having an effect on traffic flow. So there was enough of them, or many of them in many cases, that they were having an important contribution in how the city worked, how traffic in the city worked. And you see so many simulations built where some system is going to be analyzed or developed that just leave bicyclists out. And maybe it's fine in Alabama. I know our colleague, or one of them at least from Alabama, left. They said they do have some, but maybe it's okay in these situations where there's really not so many cyclists to just leave them out. Just like forget them. But in a lot of cases in Europe, especially now that cycling is becoming more important, you can't make that argument as well anymore. Another thing that's still very important, or has always been and will continue to be important, is traffic safety. And we all know that vulnerable road users are, they're vulnerable. They can get hurt more easily and do get hurt more easily in the road networks. And that's pretty much everywhere, wherever you look at the traffic statistics. So we need to have them in simulation softwares in order to be able to look at safety. And if you want to analyze safety at all with microscopic traffic simulations, then you better have realistic behaviors. So actions that they actually would do in real life. This is also an old picture. I had fun looking at my old PhD stuff and just took some of the motivations from that. This was in 2013, but already the topic was, let's develop some technologies that protect cyclists. Let's develop some technologies for cyclists. And I hope this is a field that will increase in the future as we see the bicycle as a real mode, as a group of people that need to be served. Maybe we start developing ITS systems, so really intelligent things for these road users. And if we want to do that, or think we will do that in the future, then we're going to need some tools, some simulation software that are actually capable of analyzing these systems or replicating the systems. This isn't SUMO. This is another simulation software. And this is an old picture, so it's not exactly fair. But one motivation is that we still have difficulties getting the actual behavior of bicyclists to be replicated in microscopic traffic simulation. The improvements are many, and the situation today is way different from when I started 10 years ago. I remember I opened one simulation software and the bicyclists just in the display were like 10 times taller than the vehicles, which is fine because it's just visualization. But it just went to show that nobody had ever tried to actually do this before and hadn't seen how it looked or how it worked. But that's improved. So anyways, it's not exactly a fair picture. So we have cyclists. Cyclists are unique in their behavior. They generally ride in one direction. So they have one axis of movement, but their interactions are more flexible than a car driver's are. So they interact in ways that are more similar to a pedestrian. And what is very unique about a cyclist is that they can adapt the way that they're behaving to the situation in which they're in. So if you have a cyclist who is moving in a pedestrian zone, they can adapt, they can ride slowly, they can be able to change their direction relatively quickly, not as fast as the pedestrian, but more so than a car would be able to. On the other side of the spectrum, you have cyclists riding on roadways, really in one direction relatively quickly, making very few lateral movements. So we have this kind of like a chameleon of road users that can be one or the other or both when they want to be. So how can we simulate a cyclist? Right now you have basically two options. You have the option fast, big, pedestrian. And if you follow this option, then you will use models that are developed for pedestrians. And those are usually social force based models or type models that allow the pedestrian to react to forces in their environment yeah, well, I won't talk too much about social force models, but we can later if you want to. The second option that we have is to have our cyclist as a slow and small motor vehicle. So use the modeling approaches that we have for road vehicles, car following models, lane change, lane selection models, and apply them to cyclists. This is the option that has been or is most often used in microscopic traffic simulation. So the ones that are natively implemented in the software. If you want to simulate a cyclist, use this adapted car model that works for cyclists. So how is that done in SUMO? I unfortunately missed the tutorial yesterday, but I heard that it was very focused on bicycle traffic, which is excellent. That makes me feel very happy. So you all know this, hopefully, how it's done in SUMO. There is one driving lane. It used to be the case that all road users just drove down the middle along the center of this lane. Now it is no longer the case. Now there are different sublanes within this lane, and the road users can select the sublane within the driving lane. So the longitudinal behavior here is governed by car following models, adapted, of course, with the parameters to suit bicycle behavior. And the lateral behavior is with a lane selection or a lane change model, adapted for the cyclist, basically. Okay, maybe I will just jump back a little bit. What is important to simulate for bicycle traffic? This is the conclusion of the literature review that I did in my dissertation. I looked at different categories of operational and tactical behavior. So what things do cyclists do that are maybe different than what cars do or what pedestrians do? And then I organized them into different categories. And I looked at how important these different behaviors were for traffic safety and traffic efficiency. For example, I looked at the speed. Of course, it's very important for both safety and efficiency. And so it's an important parameter that we can replicate this in our simulation models. And then on the other side of the spectrum, I tried to look at how well can we do this in the simulation softwares or the modeling approaches that we have? How possible is it to replicate? And then I tried to focus myself on the upper left-hand corner. So those are the behaviors that we can't do very well in the simulation, but they are really important if we look at safety or efficiency. And if you see the ones that are listed up there, especially in red, what seems to be important is these behaviors that show the flexibility of cyclists, or these things that get them categorized as rule-breaking, chaotic road users. So riding on interesting paths across an intersection, finding creative solutions to get across, riding against the given direction of travel at certain times, or choosing between different parts of the infrastructure. Even if you have a bicycle lane, not all cyclists are going to use this lane. Some of them will still choose to ride on the road, or some of them will ride on the sidewalk with the pedestrians. So these things are important to consider depending on your research question, but quite difficult to simulate. So this led me to my guiding aim for my dissertation, to develop models that can reflect this flexible nature, so the flexibility that cyclists have, but still work with unidirectional link-based simulation frameworks like the one that we know in SUMO. So what I developed is actually quite simple. So I even argued with myself, is it too simple to even present? But anyways, I will present it anyways, and hopefully you don't find it too simple. It's called the guideline approach, and it is a way in which we can combine this lane-based center line of a lane simulation approach with the social force approaches that are used for pedestrians. So what we have is some sort of line that a cyclist wants to follow. And this line has the same form as the center line of a lane bus. So it's just a line of coordinates or a string of coordinates. And it can, of course, be exactly a center lane of a sublane or a main lane. But what it can also be is just another trajectory that you have observed, a way across an intersection that the cyclist wants to follow. But different than the car following approaches, cyclists are not bound to this line. They do not follow along it in a one-dimensional way. They use it to determine their next point where they want to be. So social force models, if you know them, there's always a desired destination. It can be one desired destination. It can be a multiple destinations that they first have interim ones that guide their way along. And this is just a way to decide where their interim destinations are. So where is the force vector pointing towards? Then I selected a social force type model for pedestrians. It's the Nomad model from Sarah Schugendorn. And I tried to train it using calibrated it using trajectory data that I had observed in Munich. First, I just tried to use the original Nomad model and calibrated the parameters from that one. And then I developed another approach where I separated the speed component and the direction component of the model. The reason that I did that is because cyclists can't change their directions immediately. It was an easy way to be able to put some control on the changes in direction that happen every time step. So I won't go too much into detail, but just some information about how it works. There's a parameter that leads the road users to where they want to go. So get them to their desired speed that they want to be traveling at. And another term that accounts for the interaction effects that they have with other road users. So pushes away from other road users so that they don't collide, as well as obstacles and traffic lights. In this formulation, they don't change their direction according to traffic lights just so that they will stop, but I don't want to go into too much about the exact formulation because I'm not certain that this is the formulation that will work for bicycle traffic. It's just one option that I tried with the data that I had. What I did, because I didn't know what guideline a cyclist is following. You can't observe that in reality. You observe this, of course, the trajectory that they ended up taking, but why they took that, you can't really see. So I made an assumption, or I made a first step where I clustered trajectories that looked similar. Like I mentioned before, and like you probably already know, cyclists use different tactical approaches to cross intersections. They don't always use the direct or indirect left turn that we have set for them. And this approach just is an automated way to take trajectory data from different intersections and cluster them together into trajectories that are similar in the shape that they have, not disregarding the speed and any stops that they might take, just the form of the trajectory. And what I did is that I assumed all people in this cluster were trying to follow the center trajectory of that cluster, which was obviously not true, but it was the best assumption that I could make. And then I could estimate the parameters of the model. This is an example of two parameters that worked out nicely. Some of them didn't work out as nicely, but the desired speed looks very reasonable. And this relaxation time controls how fast they accelerate also looked reasonable. And then I could use this model that I estimated along with some other tactical models that helped me decide when the cyclist would take different forms of these pathways. And I tried to implement it, or I did implement it in SUMO. And then I was faced with the question, like, is this better? Is it better or is it worse? I don't know. And I think that is a main problem that we're standing at for bicycle traffic, is that we don't know exactly what we should be aiming for. What is a good cyclist model? And this is the approach that I followed in my dissertation, and I think it is a good one for seeing how good a simulator can recreate cyclist behavior. What it is, on the side, I took the trajectory data that I had at this intersection in Munich and just plotted at the top, where are the cyclists? Where are they going? Which part of the intersections are they using? Are they riding as expected on the bicycle lanes, or do we see a lot of them on the sidewalk? Are they in different locations than we expect? So there's two examples. One is with the occupancy and then the speed. And then what I did is I looked at my proposed approach that I just showed you, the implementation in SUMO, and compared each cell of the intersection that I was looking at. So are my cyclists in the simulation riding in the same places that they were in reality? Is it the same locations? And if they are riding in the same places, are they doing it with the same speed, or do they, I mean, you could think of them using many other parameters, interaction parameters, accelerations, so that you can really locate the behavior in the simulation that you have. And what you can see is that the reality is the most scattered. Cyclists are doing a lot of different things. My proposed approach was a little bit better. They could move a little bit more freely. And the SUMO approach, this was a while ago, so they don't just make left-hand turns now, of course, but it was more regular. So you can fight this by making many different paths for the cyclist to follow in SUMO, but it's quite time intensive and difficult to do. Okay, I don't know how long I've been talking, but I will continue on to my last slide before I have some discussion points. I tried to clean up the code that I used. I'm a civil engineer, so I'm not a programmer. Unfortunately, I wish I was sometimes, but I tried. I did my best effort with support also from Abuzar about the programming part to make it a little bit more useful for other people so that it could be possible to use this approach to simulate cyclists in SUMO. Okay, and then I brought some questions, some open questions that I have for myself, but also for us or you as a community. Could it be useful, or is it a useful thing to do to combine social force and lane-based models? Does it make sense to do this? Are the advantages of having flexibility and a different type of interacting behavior, so not just at within one lane or at defined conflict points, but really with all road users in the area? Is it worth it, or is the sublane approach enough? Is it doing a good enough job of simulating bicycle traffic for most of the research questions that are being tackled in or by users of SUMO? So that leads me to my other point of how do we know what is good enough? How do we validate a model for cyclist behavior? What approaches do we need to take? And what data are we going to use for that? What data is necessary, and who and how are we going to collect it? Is it possible to somehow collect it together to build this kind of fundamental knowledge that we've had for the last 40 years about car traffic and 20 years maybe for pedestrian traffic, but maybe 5 years for bicycle traffic. So we need to work on that a little bit. Would a combination be a good idea, that we can think of using a social force type model in situations where it's necessary to have this interacting behavior, and then the sublane approach when it's not? Would that be something that's feasible in a simulation environment? Would it work? And then what type of model would be the best? This is a question that's definitely open for me. I picked one. I don't tell my supervisor, but a bit randomly, and then implemented it, and it seemed to work. But of course, it would be better to compare multiple different kinds of models. Maybe it's not even a social force model. Maybe it's a different type of continuous two-dimensional movement model that is not social force. I know there's one that, one application, at least I saw for pedestrians, is discrete choice situation. Maybe that could be something useful. It would be a good field to look further in to decide how we could do that. But of course, that goes back to my first point that probably first we need some data to be able to compare and contrast the different approaches that are used. That was my first one. And then I just want to remind anyone before they look at it, cyclist model needs a lot of work. Okay, that was my presentation. I'm happy for any questions. And if it was shorter, then we can just enjoy the sun a little bit longer.